In this video, we will look at some examples of using the elimination method, which is also called Gauss-Jordan elimination, to solve systems of linear equations. Let's consider the following system of three linear equations with three unknowns: x plus y plus z equals to 2, x minus y minus 2z equals to 1, 2x plus 3y minus z equals to 0. The main idea of the elimination method is to manipulate equations so that variables get eliminated from the equations. One has to be somewhat systematic to do this elimination in order to achieve the result in a quick and efficient way. It's possible to loop in circles if one is not doing the calculation systematically. In this case, after doing elimination, one can arrive at the following system on the right hand side, which I circled in blue. This is sort of what we want to achieve with the elimination method. Here, x variable has been eliminated from the second and the third equations, and y variable has been eliminated from the third equation. So the bottom equation contains only z variable, and the equation above contains only y and z variables, whereas the first equation contains all three. I will show later how to go from the original system to this row echelon form, or it is also called upper triangular form. But for now, suppose we have done these transformations, we've done this elimination. How does that allow then us to solve the system? We use the process called back substitution. Since the bottom equation contains only z variable, we can solve that bottom equation for z. In fact, we obtain easily that z equals to 1. We can then plug that value of z into the second equation and then solve for y to obtain the y value. In fact, we find that y is -1. And then we can substitute the value of y and the value of z into the first equation and solve for x. We find that x equals to 2, y equals to -1, z equals to 1. The system has one solution and it is independent. Okay, so the unique solution that the system has is the triple 2, -1, 1. Now, let me show you how one can do the elimination that I indicated above, where we start out with the original system, which contains all three variables in each of the three equations, and we proceed to eliminate x from the second and the third equations, and also y from the third equation. It's actually a fairly straightforward process. So in order to eliminate x, we will be using the first equation to eliminate x from the second and the third equations first. Now, let's look at the x terms in our system. The first equation contains x, just 1x. Second equation also contains 1x. And the third equation contains 2x. So based on that, in order to eliminate x in the second equation, all we need to do is subtract first equation from the second. To eliminate x from the third equation, we would need to subtract from the third equation first equation multiplied by 2. Let's carry out these calculations. Also, I will be indicating at each step what exactly we are doing. Okay. Let me erase some of the results here that I have now to free up some space. Okay. So how do we accomplish this elimination? The first equation I will simply rewrite, we'll keep it unchanged. And so I write E1 in front of the first equation in the new system, and this indicates that I'm simply copying the first equation from the original system, from the previous step. X plus y plus z equals to 2. Now, to eliminate x from the second equation, we are subtracting first equation from the second. And the result will be negative 2y minus 3z equals negative 1. Please double check these calculations by doing them on your own. Now, to eliminate x from the third equation, I will subtract from the third equation the first equation multiplied by 2. And so you will see I'm writing to the left of that bottom equation E3 minus 2 times E1. What that indicates is that the equation that I am just about to write is obtained by looking at the third equation in the previous step and subtracting from that first equation from the previous step multiplied by 2. What we obtain here is y minus 3z equals negative 4. Okay. And so now x has been eliminated from the second and third equations. And our next goal is to work with the second and third equations and eliminate y variable or z variable, but we will proceed with eliminating y variable to obtain an equation that contains only z variable. My next step would be kind of not necessarily very important step, but it's just helpful to switch equation 2 and equation 3. The third equation contains, I'm looking at the y terms in the second and third equations, and the y term in the bottom equation is simpler than it is in the second equation, and that is the reason I'm going to switch second and the third equation. Strictly speaking, this step is not necessary. One can also do without this step. Okay, so I'm rewriting the first equation, x plus y plus z equals 2. And my second equation is the third equation from the previous step. That's why I have E3 in front of the second equation. It will be y minus 3z equals negative 4. And my third equation will be actually the second equation from the previous system. Negative 2y minus 3z equals negative 1. Next, we will use the second equation to eliminate y in the third equation. we will keep equations 1 and equations 2 unchanged, and I will add to the third equation second equation multiplied by 2. That is exactly what is needed to eliminate y from the third equation. Then our third equation will become negative 9z equals 2 times negative 4 plus negative 1, negative 9. And here we have achieved that row echelon form or upper triangular form where as we go down the system, our equations become sort of shorter and shorter. This is what we mean by row echelon form. Sort of have, if these boxes indicate the length of the equation, non-zero terms in the equation, as we go down the system, our equation get shorter and shorter. And that is the graphic representation of the basic idea of the elimination method, row echelon form. Okay. Once we have the system in this form, row echelon form, as I explained earlier, we can find the solution by back substitution. The bottom equation can be now solved for z. Once we have the z value, we can plug it in into the second equation, and then the values of y and z can be plugged in into the first equation, which can then be solved for x. Before we go on to another example, I'd like to comment here that here I showed you elimination where x variable is eliminated first and then y variable is eliminated from the bottom equation as well. Now this order of elimination doesn't necessarily have to be taken this way. We can eliminate variables in a different order. For example, we may have started by eliminating z variable or y variable from the second and third equations, and then we could eliminate either x or y variable from the third. And so, in fact, there is a lot of flexibility in how to carry out the elimination, although a lot of times it's being done in alphabetical order. X is being eliminated first, then y, then z, then w, or if the variables are numbered, x1, x2, x3, etc., then we eliminate x1 first, then x2, then x3, etc. Now, let's look at an example of a dependent system where the system has infinitely many solutions, and I will explain how to use parameters to represent the infinitely many solutions of such a system. So, a new example. Let's look at the following system. The first few equations are going to be exactly the same as before. X plus y plus z equals to 2, x minus y minus 2z equals to 1. For x plus 2y minus plus z equals to 7. We will see that this is a dependent system. And so let's carry out our elimination. And see if we can solve the system. Let's begin by eliminating x from the second and third equations using the first equation. So we're going to keep the first equation unchanged, x plus y plus z equals to 2. And then we're going to subtract, as earlier, as above, first equation from the second equations to eliminate x to get negative 2y minus 3z equals negative 1. And then we will eliminate x from the third equation by subtracting from that third equation, first equation multiplied by 4. And what we will get here is negative 2y minus 3z equals negative 1. So it's hard not to notice at this point that the second equation became exact same as the third equation. And if we subtract second equation from the third equation, everything is going to get eliminated, and we'll just simply get an equation that says 0 equals to 0, which is clearly satisfied regardless of what x and y and z are. And so now our system looks like this. The fact that our bottom equation became 0 equals to 0 simply indicates that our third equation was exact same as the second equation at the previous step, and really there is no need to duplicate equations in the system, because if the second and third equations, for example, are the same and the second equation is satisfied, well, then the third equation is satisfied automatically. Now, the bottom equation is valid, it's true, regardless of what x, y, and z values are. And so we can actually drop it altogether from our system. And we obtain a system of only 2 linear equations, which is equivalent to the original system in a sense that the original system and the system that we just obtained have exact same solutions. Now let's compare this situation with the one that we had previously. Earlier we had a third equation, which was negative 9z equals to negative 9, and that equation allowed us to solve for z, determine the value of z. But here our third equation says 0 equals to 0, which is, while true, does not allow us to determine the value of z. Now what that indicates is that the value of z can be chosen arbitrarily. Z is, and we say in such cases that z is a free variable. It can take arbitrary values. Check that. Choose z equals to 0. Plug it in into the second equation. Are you able to solve for y? Yes, you will be able to solve for y. Then plug in the value of y that you obtained this way, and together with z equals to 0 into the first equation. Are you able to solve for x? And again, you'll be able to solve for x. So starting with z equals to 0, you can obtain a solution of the system with z equals to 0. Now, what if you choose a different value for z? Choose z equal to 1 or -7 or any number. Repeat the same calculations, and you will see that again you can obtain a solution of the original system with the value of z that you chose. And this shows that z can take arbitrary values. Now, of course, you could say, well, why is it z that is a free variable? Why not y? And in fact, you could designate y as a free variable. However, if you choose y to be a free variable, then z is no longer a free variable, because once you choose the value for y variable and plug it into the second equation, then the value of z will be determined uniquely by the value that you selected for y variable. Now, and so either z or y variable, and in fact even x variable can be declared to be a free variable, but it's most convenient to designate z as a free variable. We can clearly see that z can take arbitrary value, and so we designate z as a free variable. Now, in order for us to calculate the value of y, we need to have that value of z. And so let's choose the value for z. Now, this value for z could be any number. We could choose 0, we could choose 1, -7, and in order for us to be able to account for all of these possibilities, let's use a letter, for example t, to indicate the value that we're selecting for the z variable. The letter t here is not a variable. In fact, it is often referred to as a parameter. A parameter is a letter in our problem, in our solutions, in our considerations, that can take arbitrary value. We do not solve for a parameter. Parameter is a letter that indicates an arbitrary number or an arbitrary choice. And in this case, t is indicating the value that we're selecting for z, and this choice can be made arbitrarily, and therefore t could really be any number. Now, suppose we selected this value t for z, then we can determine what y is. Let's plug in z equals to t into our equation, into our second equation, and then remembering that t basically stands for a specific number, we can solve for y. 2y equals -3t plus 1. And dividing by 2, we find that y equals 1 minus 3t over 2. Finally, we can plug in the values of z and the value for y expressed in terms of t into the first equation, and we can then solve for x. X plus y, and y is 1 minus 3t over 2, plus z, and z is t, equals 2. So from here, we can solve for x, and we find that x equals 2 minus t minus 1 minus 3t over 2. If we make common denominator and simplify everything, we'll get 4 minus 2t minus 1 plus 3t all over 2, which simplifies to t plus 3 over 2. These formulas that we obtain for x, y, and z describe the solutions of our system. And so here's how we can write this all down. Curly brackets indicate that there are many solutions, and we're listing those solutions in between curly brackets. Each solution looks as follows: t plus 3 over 2 for x, 1 minus 3t over 2 for y, and then t for z. And let's explain what t is. I put a vertical bar which can be read as such that, and after this vertical bar we put an explanation of what t is. T is any real number. In our context, all variables take real values, and so t is an arbitrary real number. Now, if you recall our discussion about graphical representation of systems of linear equations, what these formulas give us is the parametric equations of the line along which the three planes, which are graphs of the three equations in our system, intersect. And so we can view the following equations: x equals t plus 3 over 2, y equals to 1 minus 3 minus 3t over 2, and z equals to t. These three equations are parametric equations of the line of intersection of our three planes. And which three planes? Specifically the three planes which are the graphs of the equations in our system. This concludes this example of how to use the elimination method and the parameters to solve a dependent system of linear equations.